So good afternoon, good morning, and good evening, depending on where you're joining us from. I'm so sorry for the technical hitch that we've had as you are starting this webinar. I'm so glad, to had patience and you've waited for us, and also for creating time to be here today. Water is the foundation of life, and it supports public health, economic growth, agriculture, industry, and sustainable development. And by you joining this webinar shows your commitment to sustainable development, which is about ensuring safe water and sanitation for all. Our today's theme is reducing non-revenue water and improving water systems using digital modeling. And the reason this conversation is timely is because we are experiencing increase in population. And that means water utilities are being challenged to deliver better services with fewer resources. This means they must reduce water losses, improve operational efficiency, expand access, and manage aging infrastructure so that we are able to meet the growing demand. So at the heart of this challenge, it's a simple reality that we cannot effectively manage what we can't measure. We can't effectively manage what we can't model. We can't effectively manage what we can't understand. And that's why in this webinar, we bring to you expertise where you're able to understand the digital technologies, that in understanding that in this specific situation that you're in, water systems becomes more complex. Digital technologies are no longer optional. They are becoming essential tools for planning, for analysis, and for decision making. So digital modeling enables utilities to visualize their networks, identify inefficiencies, and predict systems performance, optimize operations, and make more informed decisions. So most importantly, it helps organizations move from reacting to problems to creating, proactively planning better outcomes. So today's webinar will explore how these technologies are transforming water management and helping utilities improve efficiency, resilience, and service delivery. So we are delighted to be joined by professionals from different areas. We have people from engineering space, we have utility managers, we have consultants, we have planners, and we have project managers, also policymakers and development practitioners. So your presence enriches this discussion, and we are honored to have you. So my name is Kwiya. I am an engineer and a partnerships and solutions architect here at Indepth Research Institute. At Indepth Research Institute, we partner with governments, utilities, development organizations, and private sector building capacity, strengthening institutions, and supporting digital transformation across key sectors, which are the water, agriculture, infrastructure, construction, development. So over 20 years that we've been in operation, we have been committed to equipping professionals and organizations with practical skills, innovative solutions, and data-driven approaches that enable sustainable growth and lasting impacts. This is why today's webinar matters. It creates an opportunity for learning, collaboration, and knowledge exchange around one of the most pressing issues facing the water sector today. So we are hosting this webinar in collaboration with modeling experts, and we'll be having Muhannad do the presentation later in this conversation. Our collaboration enables us to continue supporting utilities and organizations in leveraging digital modeling to reduce non-revenue water and improve system performance. So as we proceed, I would like to encourage you to actively participate, engage in the discussion, and share your expectations and experiences Also share in the chat box your name, the organization that you work for, and the expectations from this webinar. Also, the country that you're in is very important. So the value of this session lies not only in the expertise of our presenters, but also in the collective knowledge and perspectives presented in this virtual room. So once again, thank you for having us. I'd like to move to my presentation. So as you've seen, water utilities today are operating in increasing complex environments. So they're expected to reduce losses, improve service delivery, and also manage aging infrastructure. So that it can meet growing demand in all while working within the limited resources. So the reality is that these challenges require more than traditional approaches. They require visibility, analysis, and ability to test decisions before implementation. So this is where digital modeling and simulations tools such as WaterGems and SewerGEMS becomes incredibly valuable. This is to help us understand how these solutions are applied in practice. And I'll be introducing our guest speaker, Engineer Muhannad, who is our lead trainer for the upcoming WaterGems and SewerGEMS certification program. And before I hand it over, I'd like you to read his profile. Yes. Engineer Muhannad has 15 years of experience in consulting in hydraulics and hydrology and GIS. He has deep proficiency in Bentley platforms, including WaterGems, SewerGEMS, and WaterCAD. He's a recognized Bentley technology spokesperson driving water infrastructure advancements. He has expertise in revenue water reduction, wastewater management, and energy efficiency. He works with diverse clients, from small organizations to large owner operators, optimizing water infrastructure. So ladies and gentlemen, with claps and your favorite emojis, help me welcome Engineer Muhannad. Over to you, Engineer.
Hello, everybody. Can you hear me well? All right, so I'm going to share my screen. And, well, actually, my name is Muhannad Shaweesh. And I will be with you for like few slides. And then after that, I'm going to move to a live demo to show you how the software works. Well, actually, the reason of why we are here today is to talk about hydraulic modeling and how hydraulic modeling is saving your money. And then after that, we're going to go to a live demo, just like to show you the example from a real data that we have used from different customers around the world. So first of all, we're going to start about like, well, we are building hydraulic modeling, and then you're going to say, well, we have a cost of software, a cost of training and learning path, and then after that, we're going to become expert. But what we're going to save? I mean, where is the money saving in this? So this is like the return of investment of how we're going to get our investment back. Can you please switch off your mic? Can you mute yourself because it gives an echo? All right. So the first money-saving example that came from the hydraulic modeling is that what we can do is an optimized example from the UK. We have built the network, and then they have like amount of water. The presentation here is about United Utility in UK, but I'm going to show you as well an example from Manila Water in Philippines. After we talk about this presentation, you're going to see like multiple demo. So we can use the hydraulic model with extended period simulation to find like where the leakage is happening. A lot of people goes with a noise logger, with other methods like helium with a ball method to find the leakages. But the issue is that this is too costly, and at the same time, it takes a lot of time to find it. And if we have an extended period simulation model, we can find it fast, and then we can decide where the burst happened. We can install, like, for example, a PRV until we do fixing in order to reduce the amount of the water that is lost. Can you please switch off your mic? Hello? Sorry. So, well, from 2 bursts only, we was able to save 200,000 and 210,000 euro. And that was like before we just like take the pipe out and fix it. That's the operator phase, is actually the electricity bill. Like, for example, if I'm not sure if I'm still right, but one time I was in a visit for Nairobi Water, and when we asked about their yearly bill for electricity, it was like about I think $11 million. Imagine if you can save just like, let's say 10% of this or 20% of this bill, like $2 to $3 million every month. That is a huge amount. This is an example of a DMZ that's using 11 pumping stations in 9 tanks, and their energy cost was about 330k pound per year, which is like resulting of a 912 pound daily energy. And then we was able to reduce this from 983 to 700, which is like almost a 29% of their original energy cost. So this is like another place where we can save the energy. Mercy, or someone from Indepth Research Institute, can you please mute yourself? Hello? All right. Also, when it comes to design, since we have like a lot of consultants here, what they do normally, that's they build their design in the geographically, so they draw their network, and then they go to the Excel sheet, and in the Excel sheet they try to, for example, do the pipe sizing, and that's what we call it a disconnected design. Whenever you need to change one changing, then you have to go to the Excel sheet and then come back again, and that is too difficult. So in this case, we have like decided to go to the connected design. So whenever you have changed the location of the manhole or the pipe size, and then the system will change the rest of the pipe sizes for you, and it will give you like how your system will look like. We have do a test for one water network study for two consultants. And one of the consultants, we ask him to use the WaterGems, and we give the other consultants, and then we ask him like to do his design. And then we ask for the optimized design. And then after this has happened, the big consultants came with a solution for 4.16 million pound. But when we run it using the Darwin Designer inside the WaterGems, we get the solution under 2 million, but we choose an optimized solution for 2.14 million pound. So even when we are designing, we don't want to go for oversize. We want to design our network right. And Bentley WaterGems can do this process for us. So it depends on the iteration. Like, normally when you do a design, you start, you say, okay, let me try, for example, a pipe of a size of 100. And then probably it's not enough. Let's do 150. And then, okay, it's not working there. Yeah, well, it delivered the water over here, but some other part of the network is not delivering. And then we get like in a lot of messes. With Bentley WaterGems Darwin Designer, we create thousands of solutions. And then we only choose what we call it the Pareto front of the solution. So if it's like a benefits versus cost, so all these solutions will be discarded, and then I'm going to take these solutions only to be optimized. That is the Pareto front. Well, we talk too much. Probably now you would like to see how the software is working. And to see how the software is working, I prefer like to go to WaterGems directly. So this is WaterGems, and let's go through the first case. So let me open the leak detection, and let's discuss how leak detection is happening using the hydraulic modeling and how you can save the time. Well, I get my network here, and this is an isolated network. An isolated DMA. So this is the entrance of the DMA. And we have put a virtual reservoir over there. And then I get here like few pressure sensors. Let me change just like the color of the pressure sensor so you can see it much more clearly with orange probably. Like in green, it's not that clear. So I got my 6 pressure sensors here. And now at the beginning, I want to understand if I have a leakages or not. And I get my network in an extended period simulation. So let me run my network first. So wait, let me do it a bit smaller so I can control better. All right. So I'm going to go to the analyze and compute. And I want to compare like how much do I totally give this network. Now, the demand that I have here is actually the demand that came from the customer meter data. And in order to find if I have leakages or not, I get the demand here from the customer meter data to the network. And I have the total, I put a flow meter over this pipe here. And in order to understand if I have leakages or not, I need to compare both of the flow. So the flow total from here is what I have billed the customer for. So let me just graph it as a flow absolute. And that is what the customer had paid for. In order to understand if I have leakages or not, I have put a flow meter over here just after the reservoir. And I need to compare with this value for simplicity. Well, normally, like we have it as a flow meter. Probably it's connected to the SCADA system, or probably it's just like a built flow meter, portable flow meter, whatever it is. But I get my data now here in the Excel sheet. All right, so I get my flow meter over there. And that is my flow meter reading over the time. So in a very simple way, I'm gonna right click here, copy it and paste it. This is just for simplicity, as I told you, but we can do it in an automated process. And that's my graph here. I'm gonna take like, this is my data for the graph. And I'm gonna say, well, I need to put my observed data from the field. And that is my real supply data. And I'll paste my Excel value here. And then I'll close this one. And that is what I get out from my flow meter data, which I have it in my Excel sheet over there. All right. So now what I can see here, that is my real supply. And that is my customer meter data. And the area between these two curves represents actually the volume lost. And now we need to understand where this volume have been lost. So in order to understand this, I got here 6 pressure sensors. 1, 2, 3, 4, 5, and 6. Yeah. So you can see them here in orange color. And I need to bring this data into my Darwin calibrator in order to understand where this leakages happened. So to compare between the pressure from what I collect from the field and what's the pressure that's a customer meter data set. So in order to do this, again, for simplicity, I have the data here in the field data. And you can see here, I have like the hydraulic grade line of these sensors and the flow meter data. And I need to bring this data, 672 record into my Darwin calibrator. In WaterGems, for any external data that you need, we have a tools that's called Model Builder that's bring the data from any external data source into my WaterGems. So I need to bring the data into my Darwin calibrator over here, which is now empty. So I'm gonna use in the tools, the Model Builder. And I have specified previously here. So I'm gonna get like the data. And then when I put it in the model, so I get like 96 snapshots and I get 672 record. And then if I go to my Darwin calibrator, now I'm gonna find my data over here. Now, what I need to do is to find the leakages. And the leakages is a type of a demand. So I have to create a kind of a demand group. And let me just create a new one. I'm gonna add all my nodes to the network. So probably I can zoom a little bit out. And now I select all my nodes. So I get here like 701 nodes in this DMA that need to be tested against leakages. So in a simple way, then I can go to new optimized design run, optimized run here. And then I can go to the demand. And then here, I'm going to specify my operation. So rather than I'm calibrating a demand, I'm detecting a leakages node, I'll say, well, leakages is like acting like a sprinkler. It's a pressure-dependent demand. So it depends on the emitter coefficient. So 0 where there is no leakages, and then the maximum is 0.5 for the sprinkler coefficient, and I need to increase to the every nodes by 0.01, and I say, well, detect a combination of 10 leakages node maximum at my first try. And then I'm going to go to the field data here. And normally, like here, we get it over 24 hours. But normally, we get like the minimum night flow. And if I get back to my graph, and I can find that my minimum night flow lays over here. So probably I could get like 3 o'clock, 2:45, something like that. So I'm going to deactivate all of this one. And then I'm going to go there to the probably 2:45, a little bit up. All right, so this is 2:45. All right, and then I'm going to go to the options. I say, well, go through 50,000 trial and give me your best solution. I'm going to run this one. It will go to my network over here, selecting at the beginning maybe 2 nodes, then selecting 3 nodes having leakages, selecting 4 nodes, adjust the leakages, put the pressure dependent demand, and make a multiple collection for these 50 nodes. And each time here, you can see my fitness is reducing with my trials until like it find for me the best situation of my leakages. So, well, like let's give it about a minute more. But what it happens that it goes to every node. It like see how the hydraulic grade lines look like, and then after that it goes to change the flow and the demand of that node until it match. And you can see here with the generation, my fitness is being reduced, which is my error, until it reached to a compromised solution for this. After 50,000 trial, this gives you a very good quality of testing, and then it gives you like the minimum error one, and then you have to go to these locations to test if you have leakages or illegal connection or not. So I get my solution, and then my solution here says, if I sort this descending, says these are the nodes. I got 5 nodes that's got leakages. And now I need to understand where these nodes is. So I can go to the solution over here, and then I can export it. And I can say, well, this is like Nairobi, 10th June, 2026. All right. And then I'm going to rename my alternatives. And then when I click OK, my scenario have been created. And then I can find my scenario here, Nairobi, 10th of June, 2026 is there. All right. So now where is my leakages node? Simply, I'm going to just see my emitter coefficient. And I can see that there is a huge leakages over this here. And 2 small ones over there. And then there is a medium leakages over the pipe here. And if you go with your acoustic device after that, you're going to find the leakages at this location, most probably. So we're not eliminating fully the noise logger or the helium method or the ball method, but we just limit your place of searching where the leakages is happening. And that is like, how do we do a leak detection with hydraulic modeling? Well, like, as I told you, the other part of the network is about like pumping and pumping pricing. So what we have here is a city called Prague. And this is the touristic district of Prague. They came to us, they said, during the high season, we have no problem. But during the low season, if the meter cube costs $1 for pumping in the high season, in the low season it costs 2.5. Say, what? Why? Is your network is over pressurized? They said, we don't know, but maybe. And then, of course, it's over pressurized. It's like they got here where their pumping station is, and they have an equalization tank over this area. And then they are pumping from two big pumps. These two big pumps. And then a consultant came and they asked them that, okay, if that is the case, and then this add another two small pumps. Good idea, but this is like not how we should do it, actually. We need to do our study in a different way. So Bentley had created the pumping station concept, and the pumping station concept idea is to create for me a combination pump curve. So here I get two big pumps and two small pumps. And then if I right click here and say pump combination curve, and then it gives me all the possibility here. So this is the big pump, this is the small pump, and the possibility to operate this pumping station. It's either one big pump, two big pump, one small, one big, one small, two big, one small, and two small, and one big, and the full capacity of the pumping station, it's two small and two big. Okay. Let's suppose that we need to run at a 500 liter per second. In that case, we need to know which combination give me the best efficiency point during that time. So I'm gonna remove the head curve from here, post the efficiency, and calculate. And then that is my efficiency. And then during my design, I have to design my pumping station with a pump selection in order to have a wide range of flow. That's giving me the best efficiency. And here it's somehow good. But if I'm running at 500 liter per second, which is somewhere here, so I'm going to keep the red color one, which is efficiency 1, efficiency 6, the light green, and the cyan, efficiency 4. All right, so let me switch the others off. So I need 1, 4, and 6, and nothing else. So if I'm running at 500 liter per second, probably efficiency 4 is not required. And in that case, if I'm running at 500 liter per second, the best combination of the pump is either I switch two big pumps or one big pump and two small pumps. All right, that is good, but I need to understand how to build up my schedule, my controls, how I'm going to tell my operator to run with this schedule. In order to do this, I have in the analysis here something called Darwin Scheduler. And in Darwin Scheduler, I can create a new optimized study. And then for the pump to be optimized, I can select these pumps. But during optimization, I need to give it like my constraints. So during my constraints, I'm going to say, well, if I have pressure constraints for all my network, and then I can give it a minimum maximum pressure, a velocity constraints, and how many I allow the pumps to start and stop. For example, my maximum is 5 times per day. Yeah. And also, I have a minimum at the tank and maximum at the tank. And then I can give the tank minimum maximum here. And then when I'm done, I can compute my model. Sorry, that is steady state. And then when I'm done, I need to understand how much I'm going to pay for electricity and how my pump will operate. And in that case, we can use the scenario energy cost. And then in the energy cost, I can build my tariff, either constant or a variable tariff. And then I can compute, and then I can get for each pump what will be my daily cost. So this is my daily energy cost. For the pumps. And for example, like what is my, and then what is like my, let's say, accumulative energy cost, and how I spend these. So all this information, my graphs here. Now, this is one part of the WaterGems for operator. Let's move to the designer. So let me add well, a new file, let's say, designer list solution. All right. And let me have a look at my scenario. All right, so let me delete these two. I don't need them. Make this current. All right. I got a network here. And all these pipes that is colored, they are as-built drawing. However, I have a path where I can place my pipe. For simplicity, at the time being, I add it as a 1-inch pipe. See, if I double click over here, you can see that it's a 25.4 millimeter. All right, so any gray color pipe you can see here is just a path where I can place my pipe. It's all 25 millimeter. And now we need to understand what's going to happen if I add 189 liter per second at the junction 500. At the time being, junction 500 is at 0. And it's at 0 demand, and the system is running fine. Okay, so let's run the system and check what's happening. If I compute, and I can see that there is no problem because I didn't add any extra demand at the junction 500. If I go to the flexible table over there, and I double click on the junction, and I go to the pressure, if I check the pressure range, and then I can see that my maximum is 810 kPa, like almost 8 bar and 2.7 bar. All right. And now I'm going to ask the system, all right, what will happen if I add 189 liter per second over the junction 500? Good question, but it's not going to be a good answer. Because if I make this current and then I compute and say, negative pressure, pump exceed its maximum operating point, and a lot of problems. And if I get to the flexible table to check my junction pressures, it's going to give me something like unbalanced network. Like, I don't care what this number is, but it's an unbalanced network. All right. So now what we need to do is to redesign it to have 189 liter per second at the junction 500 and without affecting the network. All right. So how to do this? I have drawn my pipe network over there. And now I need to start to ask the system to optimize the design for me. And how do we do this? We get here something called Darwin Design. All right, so let me delete this design. It's an old one. And also I need to delete this design group because they don't relate to here. And let me start. So I need to tell the system the story in a step-by-step. And the step-by-step is a tab, is like here. All right, on a tab by tab. You have to go through them one by one. And then I'm going to create a new design, optimize design, and then the design events. What's the design events is? Let me tell you. This is a new design event. First of all, I need to adjust the demand. So I'm going to tell my system the junction 500, 89 liter per second. All junctions should fall between a minimum and maximum pressure. Let's have like 1.3 bar, for example, as a minimum. It depends on my design criteria. And I'm going to tell my system, listen, first pipe group will be must loop. And then in there, I'm going to select to loop my network. I'm going to create west, north, and south. All right. I say, well, I'm allowed to change the pipe size. One, yeah? And I put them in group. Oh, I'm going to get them from the south. And don't forget that I put this pipe in the must loop, so it's in a different group. And pipe duplicate is not allowed here. And then I build my design group. I have my cost property here. So I get the must cost. That is the pipe that you're going to design from. And that is their cost per meter. And that is the optional. With the optional, I have one with a 0 diameter here, so I can take it out of the network. And then I'm going to go to the design here. I'm going to say, give me my minimized cost. In the design, here I'm going to assign that this is a must. and the other pipe are optional pipe. So the must loop must be there. West, north, and south path is an optional path. I'm going to go to the options. I say, well, put 50,000 trial, keep the first three solutions, lowest cost. I'm going to compute. It will go and start searching for lowest cost. And it's going to tell me that my lowest cost is $175,000. And that's solution number one. If I click on solution number one, it brings the water from the north at 200 millimeter, and it brings the water, and the loop is a 200 millimeter, and then west and south will not be there. If I export this scenario, as Nairobi 10th June design. Sorry. No, I'm really bad in spelling, so sorry for this. All right. And then if I close this one, and then I'm gonna find my scenario over here. If I click my scenario, you can see that's the north path now having a different color. Yeah, you can see here, that is my average day. It was gray. It was 25 millimeter. And now if I change the scenario, it is the 200 millimeter ductile. And now let me run and compute. I deliver 189 liter per second to the junction 500. And at the same time, if I go to my flexible table, sorry, to the junction, and I can see my pressure range is vary between 791 and 280. Is this my best solution? Answer is no. And why? This is a part of optimize for the lowest cost. But I need this line. I need to cancel all this trial and error, which is like the 50,000 trial that I have gone through. But I don't want this one. I want the full line, and I want to decide where I want to stop. And then in that case, we can get back to Darwin Designer over here. I'll say, hey, Darwin, I didn't like your events. And now, in the design events, while I'm in the pressure constraint, I'm going to consider the pressure benefits. To who? It's to your best customer. And in this case, junction 500 pay part of the money. So I'm going to consider the pressure benefits over the junction 500. And I'm going to give it a budget. Rather than minimize cost, it's a multi-object trade-off. Normally, I multiply by 3 the budget of the lowest cost. So the lowest cost was 175,000. So $500,000 is fine, 600,000. And then I'm going to go to my optimized run and compute again. Sorry, 1 second. I forget to change the 3 to 20. But let me do this again. Let me finish. It's going to take 3 seconds. So I need to go to the options and change this one from 3 solution to 20. Maybe it's fine 20, maybe it's fine 15, 10, I don't know. And when I run it, multiple solution, So this 50,000, it's actually how many times you trial, and these are your nodes here. That's about what's the 50,000 over here means. And now, this 19 solution is my on one of the solution, and I say graph my Pareto front, that is my Pareto front. So I can manage to do with 175,000. But I can add a little bit more money and jump with the benefits. While here, I'm adding a lot of money without benefits. So if it's come to me, most probably I'll stop at solution number 5 or probably solution number 8. So if I have a look at this two, solution number 5, it brings the water from the west and at 400 millimeters, so I can export this one. I'll call it as 5. I'm a lazy man. Sorry. And solution number, what we say solution number what? Solution number 8. Solution number 8, also from the west. Let me check the other solution. So this is from the west and from the north. It's a bit expensive solution. Let me export it as well. It's 13. And if I close this one, and then I'm going to find my solution over there. If I click on S5, I'm going to bring the water from the west, and these pipes will be inactive. So is active is equal false. If I click solution number 13, I'm going to bring it from the north and the west. And solution number 8, it's also from the west, but at a different diameter. Let me batch run the scenario. And we can go to the flexible table again, to the pipe, and then we can see here what is our, to the junction, to see our pressure. So if I go to the junction over there, and I can see my pressure, that is how it's vary between the solutions. And all my pressure will be okay, and my network is really optimized to my needs. This is what I want to say about WaterGems. If you have any question, can you please raise it up? Hello? Am I on live? I'm not sure. Hello? Can you hear me? Hello? There is... I'm not sure if I'm online. Hello? Can you hear me?
Yes, I can hear you. Go on.
All right. Sorry. That's good. All right. So this is what I want to talk about WaterGems. I think I take a lot of time. Now, what I'm going to say that I'll be in Nairobi in September for a WaterGems course. And for the WaterGems course, actually, that is like what we do in the WaterGems course. So let me just like share the agenda with you. So it's going to be like 6 days course, not 5, because the last day will be a full project. I'm going to share the agenda with IRES, so IRES as well can share it with you. So we're going to start with the modeling fundamental. We don't need from you a previous experience. And then we're going to go through modeling to model for you your first model. Then we're going to put more effort on tank, pumps, and valve. That's in day 1. And then we're going to show model calibration, steady state, model application, system design, manual. How do we design fire protection? And then other topics like criticality analysis involving extended period simulation, the pipe renewal planner and maintenance, automatic skeletonization, real-time data and connection with the SCADA. And then how to import the data, automated model calibration as well with Darwin calibrator. And then we will go deeply into leak detection, optimize pipe sizing, and water quality. The course is going to be like 5 days and 1 more day optional for the final project. In the final project, we're going to get one of the data from Nairobi who could bring us a few parcels or any data that you prefer. And then we're going to do our design on top of these data in the last date, which is day number 6. So we're going to add 1 more day for that. And if you're interested, Indepth Research Institute is our training partner in Kenya. And as I told you, the course is planned for the first week of September, I guess, right, Mercy? Hello? And if you have any question, please let me know. Yeah, Julius?
I don't have any question.
All right, thank you, Julius. Anyone else? All right. I think from Indepth Research Institute, can we schedule another session for the sewer because it's going to take like another 30 minutes?
Yes, we can. Thank you so much, Muhannad, for this insightful and practical presentation. Yes, as you said, we have another webinar that's been scheduled. So we'll share the dates once we have confirmed them and share with the participants. Okay.
All right.
Yes, I'd like the participants to also share any question that you might be having on the chat box. In this session, we've learned how hydraulic modeling can support network analysis, pressure management, demand forecasting, leak detection, pump and reservoir optimization, and asset planning. So we've also seen the value of creating a digital representation of water network. Like any other technology, the real value comes not just from understanding the concepts, but also being able to apply them effectively in practice. And that's why we have the training scheduled in September. That's Muhannad has mentioned about. So to share more about this upcoming training opportunity and how you can participate, I'd like now to invite our Business Development Officer, Mr. Evans, who will take us through. Thank you.
Okay, so thank you everyone and good afternoon. So I want to talk about the training that we have scheduled for September. So I know everybody who's attended has seen the power and the capability of the WaterGems and SewerGEMS software, and I'm sure everybody is asking themselves what next. So if you would want to get maybe more skills in WaterGems and SewerGEMS, know how to apply it, understand the different dynamics, we have scheduled trainings in September. So for WaterGems, we have training scheduled from the 14th to the from the 14th to from the 14th to the 19th of September. And then for SewerGEMS, we have them from the 21st to the 24th of September. These trainings happen separately, but we also have a package where somebody can choose to do both. So if you choose to do both, we'll have it in one pricing. They will happen separately and you will get certifications for both. So the next section will be the Q&A section. So if there's anybody, whether you're watching from LinkedIn, whether you're on YouTube or Facebook, or you're just here in Zoom and you have a question, you can post it in the chat and we'll be able to answer it as soon as we see it. Thank you.
Thank you so much, Evans. I think as you've heard, we have a training planned up in September where you're able to plug in and learn more about WaterGems and SewerGEMS. So let me see whether we have any questions. Yes, you can share questions in the links that we shared with you. You can share questions on the chat box as well. You can also share them on email and we'll be happy to answer them. So at this point, I want to appreciate each and every one of you for being here. First, thank you, Muhannad, for the great presentation that you've made. We've learned a lot about water distribution modeling. And also to Evans for also being here and sharing about the upcoming training that we have. I want to also appreciate all the participants who have come in. We truly, truly appreciate that you created time to join us today, and we look forward to engaging more. We have another webinar lined up, and we'll be sharing them using our communication channels. Also connect with us on our LinkedIn, on our Facebook, on our YouTube, all our channels, so that you're able to stay updated with what we are doing. Also to my team that we are working together in the background, thank you so much. Kelvin, thank you so much. Eric, thank you so much. Hilary, and the entire team here at IRES. We thank you once again, and we look forward to engaging you in the future events that we'll be having. Thank you, and enjoy the rest of your day.